Okay, so hello and welcome back. So in this video we want to talk a little bit about the resonant frequency that we talked about in the previous videos, and then do a couple of examples to use these concepts a little bit to get more familiar with the concept of resonant frequency. So once I did that video and the experiment that I did in the previous video, I could not make sense of what was happening, and moreover, I mean there was still some questions hanging around in my mind. That, for example, why is basically net reactance, basically why has it been defined the way that it has been defined? For example, why is it x of L minus x of C? Why is it not the other way around? Or why is it not that why is it not the sum of the two, or some other sort of relationship between the two? Because it's supposed to be much more complicated. There has to be some sort of some much more complicated relationship between x of C and x of L. They are pretty complicated, the way that they behave, I mean. But for now, I don't want to waste time, and in order to know all of those things, you do need to know the physics behind all of this, which as of now we just don't. And but we will get there, and we will basically talk more about why this thing happens. But for now, we will just take it as the net reactance is equal to x of L minus x of C. And if that is the case, okay, so if that is this is something that doesn't make any sense to me at least right now. But or you could just think about your net reactance simply as x of L minus x of C. Why they have basically defined net reactance as x of L minus x of C, I don't really know. And it seems that, I mean, the way that it happens, it's just like that. It seems that when your net reactance is, the more that you get closer to zero, the less voltage drop is actually happening across these two, across this L and this C over here. That we can already practically see in our experiment. That the more that you get, the more that the value of this net reactance, the more that the closer that it gets to zero, the less voltage drop is actually occurring at these 2 points. Okay, so what that means is that it's kind of a representative of the reactance of these two components playing together. And that's basically how it behaves. Okay, so in the previous video we said that if your net reactance is equal to 0, then by solving basically all of these equations, you got f is equal to 1 over 2 pi square root of LC, and we call that the resonant frequency. And basically the resonant frequency is actually the frequency at which the reactance of your inductor is the same as the reactance of your capacitor. And it seems that the way that they happen, when that happens, and the reactance of your inductor is the same as the reactance of your capacitor, when that happens, then the whole basically voltage drop across the two components both together is at a minimum. And that's basically why you got that graph of output versus frequency for this circuit, which was basically something like this, okay. And this peak actually happened at f of r, and this was f of in, and this is v of out for this circuit over here. So that's basically what we can understand from this right now. Although I don't understand it completely, but we will have to get more into the physics behind this, and more into the basically more into the electronics, the theoretical electronics behind this, and we will understand that's not that big a deal. So that's that. Now we have a couple of examples here. Let's see. Okay, so now let's suppose that you want to calculate the resonant frequency for the circuit shown using the capacitor and inductor. Okay, so let's say that you have 7.3. So let's say that you have the same circuit. Let's say that you have the same circuit over here, and you want to calculate the resonant frequency for this circuit, and the values that we have over here are, let's say that your capacitor is 1 microfarad, and your inductor is basically for example 1 millihenry. Okay, so if that's the case, and the circuit is the exact same thing that you have over here, so then your basically f of r, as we said, is equal to 1 over 1 over 2 pi the square root of LC, which is equal to 1 over 2 pi square root of L, which is basically 1 millihenry, is 10 raised to the power negative 3 Henry times 1 microfarad, which is 10 raised to the power negative 6 farad, and that's equal to, that's the same thing as 1 over 2 pi the square root of 10 raised to the power negative 9, and that's basically 10 raised to the power negative 9. If you calculate that using a calculator, what you would get is, let's do it this way, so 2 pi square root of 1 into 10 raised to the power negative 9, and that's equal to 1.99 into, did I do? Okay, so that's 5032.9 hertz, which is the same thing as 5 kilohertz or so. So approximately 5 kilohertz. Okay. So that's the resonant frequency, for example, for this circuit. And suppose that you wanted to do the same thing for another circuit, the same circuit but different values. So for example, your capacitor is 16 microfarad, and your inductor is 1.6 millihenry. Okay, so in that case, your resonant frequency is 1 over 2 pi the square root of LC, which is equal to 1 over 2 pi the square root of L, which is 1.6 millihenry, so times 10 raised to the power negative 3 Henry, times your C is 16 microfarad, so 16 into 10 raised to the power negative 6 farad. Okay, and this is equal to 2 pi into the square root of 1.6 into 10 raised to the into 16 into 10 raised to the power into 10 raised to the power negative 9, and take the reciprocal of that, you will get 994.7 hertz. 994.7 hertz. Okay, you can take that as 1 kilohertz or so, because you usually don't get so much precision on a normal signal generator anyway, or on in a circuit. I don't know, depending on the circuit that you use, you might get basically precision all the way up to 2 significant figures or so, but not more than that. So that is that. Let's see what that is. Okay. So now let's do a couple more examples here. These are all related to the same formula. Let's say that, for example, your capacitor is, let's say that your capacitor is 0.1 microfarad and your inductor is 1 millihenry. Okay, so then your resonant frequency is equal to 1 over 2 pi, the square root of LC, which is equal to 1 over 2 pi, the square root of L in 1 millihenry, 10 raised to the power negative 300 times 0.1 microfarad. So that's 0.1 into 10 raised to the power negative 6, so that's 10 raised to the power negative 7. So that's the same thing as 1 over 2 pi, the square root of 10 raised to the power negative 10. Okay. So now you have 2 pi into the square root of basically 10 raised to the power negative 10. And take the reciprocal of that, you will get 15,915.5. 15,915.5, and that's something about 15.9 kilohertz. 15.9 kilohertz, or you can take it as 16 kilohertz if you want to, depending on your situation. Okay, and then let's say that the values that you have are, I don't know, probably 1 microfarad, 2 millihenry. So if C is equal to 1 microfarad and your L is equal to 2 millihenry, then your resonant frequency F of R is going to 1 over 2 pi, the square root of LC, which is equal to 1 over 2 pi, the square root of, for example, 2 millihenry, 2 into 10 raised to the power negative 3, times C, which is equal to 1 microfarad, 10 raised to the power negative 6, and that's the same thing as 1 over 2 pi, square root of 2 into 10 raised to the power negative 9. So that is 2 pi. That is 2 pi times square root of 2 into 10 raised to the power negative 9. Take the reciprocal of that, and that's 3558.8. 3558.8, and that's the same thing as 3.6 kilohertz. 3.6 kilohertz or so. Okay, so that's basically how you do resonant frequency. So in the next video we will do probably an experiment with the same type of circuit but in a different sort of configuration, and we will do some calculation there as well. So I'll see you in the next video. Thank you.